So we have a pretty straightforward algorithm in this section. Really, the only difficulty you're going to have in this section is setting up models if there's application problems and actually calculating integrals, because the steps are quite straightforward. So we're going to give you an example here about using integrating factors, and I'm going to ask you to find the general solution to the following differential equation. dy dt plus 2 over ty equals t minus 1. All right, so again, I would like to point out this is a linear differential equation, right? The derivative is by itself. There's nothing being done to the y in terms of functions. And yeah, there's a function of t next to y, and yeah, there's a function over here. It's non-homogeneous. Yeah, this is all fine. We have a linear differential equation. It's not autonomous. It is not separable. October. Stop that. October's clawing at my window screen. In typical math lecture fashion of animals going nuts. So what we're going to do is integrating factors. So remember, we have to find the integrating factor, which is what this is. We'll multiply our ODE by the integrating factor. We'll use the product rule, then we'll integrate and we'll solve. Let's see what that looks like. So first we're going to find the integrating factor. The integrating factor is going to be e to the integral of g dt. What was g? G is whatever function is next to y if it's in the standard form. So we're going to say, all right, mu of t equals e to the integral of g of t, which is 2 over t, dt. Just like so, that's it. And then we'll do some integration, right? This is going to be e to the natural log, 2 times the natural log of the absolute value of t, plus a constant. And then that constant really is just c e to the, we can rewrite this, right, using properties of logarithms. This is the logarithm of the absolute value of t squared. The absolute value of t squared is just the same thing as t squared. T squared is always positive, so we don't need the absolute value anymore. And then these are inverse functions. October, please do not eat my notes. I need them. Well, maybe not for this video, because integrating factors is so straightforward. And we get some cancellation here, right? It's any constant times t squared. So there's infinitely many integrating factors that are going to work. You don't need them all. Right? For the general solution, yeah, there's going to be a plus c that you need. But for the integrating factor, any of these integrating factors is going to work. You could try with any of them. So I'm just going to choose c to be 1. All right? C can be whatever we want. You could have c be 5. See if we get the same answer. All right? So I found my integrating factor. Now I'm going to multiply the differential equation by my integrating factor. Okay, so I'm multiplying everything by t squared. And when I do that, what am I going to get? I'm going to get t squared times dy dt plus t squared times this, which is going to be 2t times y equals t squared times this. And hopefully I did my math right. T squared times this is like 2t, yep. T squared times this is t cubed minus t squared. Yep, great. Wonderful. And you know, sometimes there's an easier number for c, right? Like if this differential equation had 2's everywhere, maybe I would want my integrating factor to be 1/2 t squared. That would be fine too. Because of course, right, I can multiply both sides of this equation by 2 or 3 or half, and it'd still be the same differential equation. It'd be still just as easy or hard to integrate. All right, step 3 was to use the product rule. So we notice that the left-hand side is the product rule. The left-hand side is what happens when you take the derivative of t squared times y. Is it not? Do you not believe me? Check it out. Derivative of t squared, so, you know, derivative of the first, 2y, times the second. Sorry, 2y. Derivative of the first is 2t times the second, which is y. Have that right here. Plus the first times the derivative of the second. Have that right here, right? The whole point of integrating factors is to get the product rule. That's what we derived kind of in the last video. All right, so that's great because what do we have? We can integrate both sides with respect to t. Right? So if we do that, again, that's going to be step 4, integrate and solve. We're going to get the integral of the derivative of t squared y dt equals the integral of t cubed minus t squared dt. Well, what's the integral of the derivative of something? Just itself, plus c. All right, so we'll have t squared times y plus c. Integral of the right-hand side's no problem. A quarter t to the 4th minus a third t cubed. We'll just put the c over here. And we can divide everything by t squared to get our answer. So we're going to get y is equal to a quarter t squared minus 1/3 t plus a quarter of c is just some new constant. Well, there we go. We have a solution. And again, we could check our solution. We could take the derivative of this, which is going to be half t minus a third, plus 2 over t times this, and it will simplify to t minus 1. No problem. That's it. All right. So we notice that what we have here is, wait a minute. Oh, I did mess up a little bit. All right, we divided everything by t squared. Dividing a constant by t squared is not another constant, right? It's a constant divided by t squared. All right, cool. Now we are good. I was a little worried there for a second because I was going to talk about qualitative analysis. But yeah, right. You don't necessarily know where remember the extended linearity principle, the linearity principle for non-homogeneous differential equations. And that said, your solution, your general solution to your non-homogeneous differential equation was just the homogeneous general solution plus any particular solution of the other equation. And again, you kind of get that lost a little bit here. We can't quite see which piece is which when we're using integrating factors. But of course, we could still find out which part's which, right? What's the homogeneous version? The homogeneous version is just what happens when this is equal to 0. So you can see, yeah, if we solved this differential equation, what are we going to get? We're going to get the c over t squared. That's going to be our, sorry, not the c over t squared. Actually, I think it is the c over t squared, right? Because we're going to get 1 over y and 1 over t. Oh, you could find it out. You could find it out. But I'm not going to spend time working on it on this video. That's pretty much it. That's all integrating factors is, right? And again, sometimes this can be hard or impossible. Sometimes this can be hard or impossible. So integrating factors can have some problems, but again, the algorithm, right, the steps are pretty straightforward. You don't have to do a lot of guesswork. You just have to be able to do integrals. That's pretty much what we have. The next video also, what can go wrong? Again, it's probably not very surprising, but we'll get some more practice with integrating factors. See ya.